Hey everybody, it's Miss Berry. We're going to try this the third time I'm trying to record this, but I think we've got it this time. All right, so in this section we're going to go over, we're continuing to talk about polynomials. This section is called Locating Real Zeros of Polynomial Functions. So just a reminder, the word zeros, this word is known by many names. This is also called x-intercepts, also called the solutions to the polynomial equation. And it's also called the roots. So zeros are also called x-intercepts. They're also called solutions when you're talking about equations. And they're also called roots. These just refer to the spots or the places on the places where the polynomial crosses the x-axis. So we're again continuing to talk about polynomials. In this section, we're going to specifically talk about two theorems that allow us to locate x-intercepts of polynomials. We're going to first talk about the rational zero theorem, which I will sometimes abbreviate RZT, and then the intermediate value theorem, which I will abbreviate IVT. All right, so let's jump into the rational zero theorem, and you may need to pause the video to write down these theorems as we go through them. All right, so the rational zero theorem says, if f of x is a polynomial with integer coefficients, then any rational zero must be of the form p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. All right, so let's talk about how we can use this theorem and the limitations of this theorem. So again, one of the limitations here is that the polynomial itself has to have integer coefficients. So that means that your polynomial can't have coefficients like, for example, 1/2 x squared. All right, so you couldn't have this type of polynomial here because that coefficient is not an integer. All right, so you have some limitations in the type of polynomials that you can be looking at. And also the second limitation is that this is only going to tell you the potential rational zeros. Okay, so potential meaning they might be zeros, they might be x-intercepts, or they might not be x-intercepts. We'll have to check, but it does give us a starting place for where to look. And then secondly, it can only tell us the potential rational zeros. And again, the word rational, that here that's referring to rational numbers, numbers that can be written as fractions. All right, so any rational zero has to be of the form p over q, where p is a factor of the constant term, that's the number on the end, and q is a factor of the leading coefficient. We talked all about the leading coefficient back in section 5.1. All right, so let's look at our first example. Consider the following polynomial. T of x equals x cubed minus 3x squared minus 3x plus 9. Use the rational zero theorem to list all the potential rational zeros. All right, so again, remember, P is the factors of the constant term. Q is the factors of the leading coefficient. What's the leading coefficient here? What's the number in front of x cubed? There's no number there, but we know that there's an understood 1 there. All right, so Q is 1, or Q will be the factors of 1. All right, so what are some things that multiply to give you 9? You could do 1 times 9 or 3 times 3. But you could also do -1 times -9 or -3 times -3. All right, so P is going to be plus or minus 1, plus or minus 3, plus or minus 9. All right, so positive 1, negative 1, positive 9, negative 9, positive 3, negative 3. All right, and then we can actually shorten this just by writing the plus or minus at the front, and then we just know that that plus or minus applies to everything. All right, so that's how they'll have you write it on the homework. Now, let's list out what are the factors of Q. What are the factors of 1? You could do 1 times 1 or negative 1 times negative 1. So again, plus or minus 1. All right, so now we're going to list the potential rational zeros. Again, it says the RZT, the rational zero theorem, says that any rational zeros must be of the form P over Q, where P is a factor of the constant term and Q is a factor of the leading coefficient. All right, so we have to form these into little fractions, P over Q. Put the plus or minus at the front. All right, so here's P, here's Q. P divided by Q. 1 divided by 1 is 1. Moving on to the next one. 3 divided by 1 is 3. 9 divided by 1 is 9. All right, so again, this was 1 over 1, 3 over 1, 9 over 1. And we just simplified. All right, so there are our potential, these are the potential rational zeros. Now, how do we figure out if these are actual rational zeros or not? Really simple. We can go off here to the side. What we're doing here, we're gonna find the actual. This is not part of the homework question, but this will help us with step 2. So how we figure out which ones are actual rational zeros is you're going to go to your y equals screen, clear out whatever you got in there, and type in this function right here, x cubed minus 3x squared, x cubed minus 3x squared, whoops, let me just start over, x cubed minus 3x squared minus 3x plus 9. All right, now you're going to go to your table. I was just messing with some of my settings, so let me fix that really quick. Oops, I hit the wrong thing. Sorry. It's going to come back down. No? All right. There we go. So now you're going to go to your table. So second graph takes you to the table. Second graph takes you to the table. All right, now we're going to look at each one of these. Let's list them out. We had positive 1 and negative 1, positive 3 and negative 3, positive 9 and negative 9. All right, we're going to look at each one of these values on the table and see if they give us back a 0 as the y value. If they do, then that means that they're a 0. They're an actual 0. All right, so positive 1 is right here. Gives us back 4. Okay, so that is not an actual 0. So I'm going to cross it out. That one doesn't work. What about negative 1? It gives us back 8. But that one doesn't work. What about 3? Oh, that one works. Negative 3. You might have to scoot your table up if yours didn't show up. Oh, sorry, you guys. I'm not looking at my calculator. I'm looking at the screen. You might have to go up and down on your table to find these values. All right, negative 3 is right here. Nope, that doesn't give us back 0. What about 9 and negative 9? All right, 9 doesn't work for sure. Let's go up to negative 9. Nope. All right, so neither one of those works. All right, so out of that list, we only found one actual 0, but that's okay. All right, so the rational zero theorem helped us to identify one of the zeros of this function. Now, how do I know how many zeros I'm going to have? It's really simple to figure out how many zeros you're going to have. You go to your original polynomial and look for the highest exponent. Remember, that's called the degree. All right, so here the degree is 3. Degree is just the highest exponent. The degree tells you how many x-intercepts you're going to have, how many zeros you're going to have. So we're going to have 3 in total. We just found 1. All right, so that tells us that there's 2 more. This was the only rational one. All right, so we found that rational 0. Now we're going to have to do a little bit of fancy footwork to find the other 2, the other 2 zeros. All right, but we're going to use this. This is our starting point for finding the other 2. All right, so it says step 2, use polynomial division and the quadratic formula, if necessary, to identify the actual zeros. All right, so we've already found 1. We've got our first one, is 3. All right, so this is where we'll list our actual solution or our answer. We got our first one, is 3. And again, we knew that because when we plugged it into our, or we looked at the table in our calculator, 3 was the only one that gave us back 0. All right, so we're going to use this number here to set up synthetic division. All right, so 3 is going to be the little number that goes in the box. So whatever that 0 was that you found, that goes in the box. All right, so that went here. And then again, for synthetic division, we're going to go up here and take the coefficients of our polynomial. So that's 1, -3, -3, 9. 1, -3, -3, 9. All right, so the way synthetic division works, you always skip a line. So blank line, long straight line, drop down that first number. Now start multiplying. 3 times 1 is 3. Then add or subtract. -3 plus 3 is 0. Multiply again. 3 times 0 is 0. Add or subtract. -3 plus 0 is -3. Multiply again. 3 times -3 is -9. Add or subtract. 9 minus 9 is 0. All right, so here's our quotient. We knew that our dividend was a degree 3. That tells us our quotient is going to be 1 degree less. That means degree 2. So that's going to be x squared plus 0 times x minus 3. Remainder is 0. All right, so we can simplify this. 1x squared, that's the same thing as x squared. 0x, that cancels out, that goes away. Then minus 3. All right, so that's our quotient. Now that quotient is gonna help us out because that's something that we can easily find the zeros of. All right, so we're gonna take that quotient there and find the zeros. So find the zeros. All right, so set that equal to 0. This is a quadratic polynomial. We have lots of methods for solving quadratic functions, or solving quadratic equations, I should say. I'm going to use the square root method here, so I'm just going to move that 3 over. So x squared equals 3. I'm going to take the square root of both sides. Square root is going to get rid of that square on the left. So take the square root of both sides. Don't forget to do plus or minus of the number side. On the left, a square cancels with a square root, leaves you with x equals plus or minus the square root of 3. Okay. So going back up here, we're going to write our solution. So there's our last 2 zeros, positive square root of 3 and negative square root of 3. All right, so we had 3, positive square root of 3, and negative square root of 3. Again, we knew that we were going to have 3 zeros because the degree was 3. All right, so 1, 2, 3. There's our 3 solutions, our 3 x-intercepts, our 3 zeros. Okay. Let's look at another example that will be a little bit easier. Okay. Consider the following polynomial. V of x is x to the fourth plus 7x cubed plus 11x squared minus 7x minus 12. Use the rational zero theorem to list all of the potential rational zeros. How many actual zeros should we have? What's the degree here? Degree is 4. Degree tells us how many zeros we're going to have. So there should be 4 in total, 4 zeros of this function. All right, so let's start using the rational zero theorem. All right, we know that P is the constant term, factors of the constant term. Q is factors of the leading coefficient, which we know is 1. All right, so what are some things that multiply to negative 12? So do the plus or minus in the front. Or let's just think about 12. What's some things that multiply to 12? 1 and 12, right? 4 and 3, 2 and 6. I listed them in order. You don't have to. It's okay if you list them out of order. Doesn't matter to me. Doesn't matter to Hawks. So it's okay if you didn't list them in order like I did. All right, what are some things that multiply to give you 1? Just 1 and 1, right? So plus or minus 1, because you could do 1 times 1 or negative 1 times negative 1. All right, now we're going to form our fractions, P over Q. Remember, the rational zero theorem said rational zeros can be written in the form P over Q, where P is a factor of the constant term, Q is a factor of the leading coefficient. All right, so P over Q. Plus or minus out front. All right, so starting here. 1 over 1 is 1. Sorry. 2 over 1 is 2. 3 over 1 is 3. 4 over 1 is 4. 6 over 1 is 6. 12 over 1 is 12. There's our potential rational zeros. We can go over here, figure out which ones are actual zeros. That'll help us for the next step. All right, so go to your calculator, clear out anything you got in there, in your y equals screen, I mean. Type in your polynomial, x to the fourth plus 7x cubed. You can do this without a graphing calculator. It just would take you way longer because you would have to plug in each one of these into v of x. So you'd have to plug in 1 for x, plug in negative 1 for x. It'll just take you forever. Minus 7x minus 12. All right, so then go to your table. Second graph takes you to the table. All right, so let's see, I'm going to start up here with negative 12. Negative 12 does not work. What about, let's see, negative 6? Nope. I'm kind of working backwards here. 4, negative 4. Okay, that one works. Negative 4 works. Negative 3 works. All right, scooting on down. Negative 2 does not work. Maybe it would help you more if I would actually list them all out first. I think that's better. That's what I did last time. All right, so you could have positive 1, negative 1, positive 2, negative 2, positive 3, negative 3, positive 4, negative 4, positive 6, negative 6, positive 12, negative 12. All right, so we just went through a few of those, and we went ahead and ruled out negative 12, negative 6, no, negative 4 worked, negative 3 worked, negative 2 does not work, gives you back 6. All right, negative 1, all right, that one works. All right, now we're moving into the positives. Positive 1, that one works. What about positive? Positive 2. Nope, that one doesn't work. Positive 3. Nope. Positive 4. Nope. All right, got to check 6 and 12. 6 does not work. What about 12? Does it work? No. All right, so let's see. 1, 2, 3, 4. How many zeros did we say we were going to have? Since it was a degree 4, we were supposed to have 4 zeros. And we were able to find them all 4. 1, 2, 3, 4. So for step 2, which says use polynomial use polynomial division in the quadratic formula if necessary to identify the actual zeros. We don't even have to do that because we were able to use the rational zero theorem to identify all 4. All right, so we just list those out. All right, so our actual zeros were 1, -1, -3, -4. All right, so if you look at the degree is 4. That tells you how many solutions you should have, how many zeros you should have. So we were able to get all 4 with the rational zero theorem. Okay, let's look at the intermediate value theorem and then we'll wrap this up. Right, intermediate value theorem, IVT. Intermediate value theorem says if f of x is a polynomial with real coefficients, so a little less strict here, the coefficients can be any real number. It doesn't have to be integers like with the rational zero theorem. All right, so if f of x is a polynomial with real coefficients and a and b are real numbers, just notes here that a has to be the smaller number of the two. A is less than b. So f of x is a polynomial, a and b are real numbers. If f of a and f of b are different in sign, then there is a 0 between a and b. Okay. Now this kind of sounds a little complicated, but it's actually really simple concept. And it says that if you have a polynomial, say this is our polynomial, and we'll let this be a, this be b. All right, so it says if you have this polynomial and you went over here to a and you said, okay, where's the graph at the x value of a? It's right up here. The graph is above the x-axis, so that is positive. Down here at b, if you go down to the graph at the x value of b, it's down here. This is below the x-axis, so it's negative. All right, so what the intermediate value theorem says is that if you have one positive y value and then another negative y value, then at some point, since this is a polynomial, it must have crossed that x-axis somewhere in between those two values. All right, so in order for it to have changed sign, went from positive to negative, then it must have crossed the x-axis, and therefore it has a 0 between those two x values, a and b. All right, so let's look at an example. It says, this is going to be super easy. Find the value of the following function at x equals 2 and x equals 3. Does the intermediate value theorem guarantee that the function has a real 0 between those two x values? All right, so here's the function. We're going to let our calculator do all the work here. So we're going to go to our y equals screen and type in our function, negative x cubed plus 2x squared minus 2x plus 7. All right, then we're going to go to the table. So second graph takes us to the table. All right, so if we plug in 2, gives us back 3. If we plug in 3, gives us back negative 8. So are those function values different in sign? Yes, one is positive and one is negative. All right, so since they are different in sign, since those function values are different in sign, then there is a 0 between 2 and 3. So does the intermediate value theorem guarantee that there's a real 0 between 2 and 3? Yes. You would only answer no if these were both positive function values, like if you had 3 and 5. So if they're both positive or if they're both negative. Right, so what you want here is for them to be different in sign, one positive, one negative. All right. So hopefully this recording got everything on the screen. If you have any questions about section 5.3, please let me know. Otherwise, I'll see y'all in my next video. Have a good day.